All right. So, hello. Uh, we will be revising today very quick topics about um, statistical optics. So, we'll start with some basic um, theory about probability. Okay. So, not we are not going to go into the really the basic things, but we will start with something like probability density function or a random variable. Okay. So I'll give you just what is required for you to start with studying statistical optics. So, um, so the probability of an event A is defined as the limit of the relative frequency as the number of trials capital N increases without a bound. So what is saying that the probability of an event A is given by n divided by capital N, where the limit of capital N goes to infinity. Okay, so this is called the relative frequency relative frequency. Okay, but this definition of probability, is not complete because, or you can say this is not so much acceptable because for this to happen practically you'll have to do infinite number of experimental trials. Okay, so we would be adopting the axiomatic approach which assumes something to be true, and then things build up on that. So the first one in that is uh, any probability PA should be greater than equal to 0. Okay, so now we are starting formally. So uh, any probability of an event to happen, yeah, of an event A to happen, it should be greater than or equal to 0. The second one is if S is an event that is certain to happen, then the probability of that event must be 1. So if say if an event S is certain to happen, then the probability of the event S to occur is equal to 1. So the basic structure of probability must satisfy these axioms. Okay, now if A1 and A2 are mutually exclusive events, okay, that is the occurrence of one, say A1, and the occurrence of the other, say A2, does not, the occurrence of A1 guarantees that A2 does not occur. So that is the same way of saying, that is the other way of saying that A1 and A2 are mutually exclusive. Okay, so if they are mutually exclusive, then the probability of A1 to happen or A2 to happen is given by the probability of A1 plus probability of A2. Okay, you can see here that since the occurrence of A1 is not at all dependent on A2, and the occurrence of A1 guarantees that the other does not occur. Okay, so in this case the probability of happening occurrence of A1 or A2 is given by the individual sum of individual occurrence probabilities. Okay, so now we'll move to the definition of the very simple definition of the random variable. Okay, so to every elementary event A, we assign a real number UA. So suppose there is an event A to occur. For example, you have a coin, okay, and suppose one side you have heads and other side you have tails. So there can be two possible events here. Okay, so it may be H and T. Okay, similarly, if you throw a dice, excuse me for my bad drawing. So if you throw a dice, okay, you have 6 possible outcomes. So that can be 1, 2, 3, 4, 5, and 6. Okay, for its 6 faces. So your experiment or your event can be anything, and depending on the type of your event, you can have what you call in common language is the sample space. Okay, so for every elementary event A, so I call the general form of event H or T, or in this experiment 1, 2, 3. Okay, we call it A. So the occurrence of an elementary event A, we assign a real number, okay, UA. That real number is the choice of us. I mean, that's our choice. We can assign any real number. Okay, for example, excuse me for the sound in between. So we can assign a heads as 0, a tails as 1, or we can assign a heads as 1, tails as 2, or we can assign these outputs as 0, 1, 2, 3, 4, 5, or we can keep it like 1, 2, 3, 4, 5, 6. So there is difference between this and this. This is basically your sample space, the outcomes, and these are the assigned numbers, real numbers, okay, corresponding to each event. So for a given event, elementary event, you have a number we denote by U. So U, the value of U will depend on A. If you change that event, so here if there is some occurrence of heads, you assign a number, given number. Okay, so if you change that event, your U should change. Okay, so that depends on your event. So U is a function of A, and this mapping can be your definition. So the what is the random variable? So random variable U, we assign random variable by U. Okay, so the random variable U consists of all possible UAs together with an associated measure of their probabilities. Okay, so you can imagine a random variable as a set, okay, where all the possible UAs are given, and associated with that, whatever probabilities it has. Suppose in case of tossing of a single coin, you have the U values are 0 and 1, okay, and the A's are heads and tails. Okay, so UA would contain 0 with probability half. So the probability information is there along with U. Okay, and also the random variable U for this event would also contain the other element would be 1 with probability half. And similarly in this experiment, and if you consider let's say you consider say this one as your the real values, what you can say is the random variable U would contain a 0 along with the information that 0 is occurring with probability 1 by 6. Similarly 1, 2, 3, 4, 5, each with probability 1 by 6. So for example, suppose there would be some other experiment where it's like the outcomes are if it's an odd number. So if it's an odd number, there can be different values and there can be different probabilities. Here you're seeing that each element is having same probability. Okay, so we'll move forward, and Okay, so next we gonna discuss the probability distribution function. So what is a probability distribution function? So this is for our convenience. We define a probability distribution function. So we define. I hope these random variable and probability definitions are very clear. So we define this probability distribution function as denote this by a function f, okay, with a subscript of the random variable u, and which will be a function of those real values assigned for each event. Okay, so we write this fu of u as the probability of u having value less than u. Okay. All right. So if you want to find, for example, in this case, if you want to find the value of this fu at point small u, so let's say this small u here is, let's say small u here is 2. Let's take 2. Okay. All right. So what will be the value of this fu of small u? Okay. So that would be the probability of having an occurrence where the random variable has a value less than or equal to u. So the probability of occurring of this part is what is the value of fu. Okay. So that must be half, you can see. Okay. That must be 1 by 6 plus 1 by 6 plus 1 by 6. That gives you 3 by 6, and that is 1 by 2. Okay. Now there is something important important property to for this probability distribution function. They must satisfy these 3 properties. So the first one is that fu of u must be non-decreasing to the right. Okay, so that simply means that if you want to find the probability distribution function capital fu at this point, the value of fu must be smaller than the case when you go towards the right and say you try to find the value of probability distribution function at this point, as this value of small u. Okay, so as you go towards the right, the value of fu must increase. Okay, the second one is that fu of u, okay, I'm sorry, u equals to minus infinity or tends to minus infinity must be 0. Okay, if you go to the extreme left, so probability of occurrence of nothing must be 0, and then the next property to be satisfied is the probability of occurrence of u equals to plus infinity must be equal to 1. That simply means is that the probability of occurrence of everything, so when you are towards the extreme right, okay, you are basically at plus infinity in this language, so occurrence of everything must be 1. Okay. Next we would be discussing the probability density function. So this is probability density function. We denote it usually by p capital U as a subscript, and a function of small u. So this is just a derivative of the probability distribution function. Okay, so p of capital U, p subscript capital U of small u is defined as, so this is the definition, the symbol of definition, okay, that this p is defined in that way. So this is just a derivative with respect to small u of the probability distribution function you have seen earlier in this video. Okay, so this is very important. We can highlight this. Okay, this one is very important to remember, that probability density function is the derivative of probability distribution function. Okay, so there is one property which would be mathematically needed in future in many places, is that how do you find the probability of occurrence of something between some region. Okay, to go to that level, we will start with very elementary definition of derivative. Okay, so what you're going to do is we write p u of small u as f u of u. How do you define derivative? I'm sorry, my battery is low. I'll have to connect the charger. Okay, now it's fine. So the definition of this derivative is minus f u of u minus delta u, okay, and divided by delta u. The other way is to use here u plus delta u and fu here, and again the same. So basically you can use anything. This is the first principal definition of derivative. Okay, so this is not actually the full definition. The definition is when you put it as small delta u tends to 0. Okay, so that basically gives you, for a given curve, this basically gives you the say that you have an x and y coordinate system, and this one is a function. So basically suppose for this part you want to find the slope. So what you do is this minus this value, the y, divided by this x value. So this delta u serves as the change in x, and this serves as the change in y. Okay, so you know that well enough, I guess. Okay, so for small, so if I already say that delta u is already small, I can not continue writing this limit delta u tends to 0 symbol. So from here you assume that delta u, I'm sorry again, delta u tends to 0. Okay, this is true from now onwards. Okay, so if you bring this delta u towards this side, what you get is p u delta u is nearly equal to fu of u minus fu of u minus delta u. Okay, now what you see, what you observe here is that this is the probability of having the value less than equal to u. Okay, so let's draw a u line. Okay, so this, suppose let's start from 0, 1, 2, 3, 4. Okay, so suppose this is your the value of possible values of u, the random, the small u, which was a function of the outcomes. Okay, so suppose you define this as u here. Okay, so this is the probability of having values less than equal to 2. Okay, and this, suppose delta u is very small, but let's say this Okay, this is a discrete one example, so we'll take a discrete uh, form of this definition, but actually this is for a continuous. So your small u consists of many points as a continuous way. Okay, so suppose your delta u is 1, and so this fu minus delta u is the probability of having values less than equal to 1. So if you subtract the two, what you get is probability of having values between 1 and 2. All right, but that we can write as equal to, just writing in another way, of u having values from u minus delta u to u. All right, so it follows that if you integrate everything from minus infinity to plus infinity, what you should get is this. How does it come? See, this PUDU gives you the probability of occurrence from u minus delta u to u. So very small section of probability. Okay, probability of occurrence between in this region. So if you integrate, okay, if you move here and here and here and add all the things, you should get a 1. That's the basic definition of probability you have studied earlier, like this. Where was that? Oh, here, here, here. If you go to the extreme right and consider everything, you basically consider all the values, you should get a probability 1. Okay, or you get a probability, because this is basically probability. Okay, I hope that is clear now. And in a similar fashion, if you want to find the probability of an event being in between A to B, how do you do that? You start from A, go to B, and in that region you integrate this probability you integrate this probability density function in this region. So this one is also very important. You should underline this. Okay. Okay. Now, not always you have a continuous probability density function. In case you have a probability density function of discrete nature, what you can do is, I'm sorry again, what you can do is, for discrete nature, the P U excuse me, U is defined as, basically you can relate the two as k equals to 1 to infinity, and this is P uk delta u minus uk. Okay, where this uk's represents the discrete set of possible numerical values of u. So this capital U, the random variable, contains values, okay, small u, and earlier it was continuous, but now since it is discrete, you need to use this u minus uk. So when your u is not equal to the values under this, so uk's are only here, okay, it will give you a 0 contribution, and when this is equal to 1, it will give you this one becomes 1, and so you just add all the probabilities, okay, till this uk. All right, so we are about to finish this part of this lecture. we'll just introduce two types of density functions. Okay, we'll just write down the general expression of these two density functions, which are very important in statistical optics. The first one is the Gaussian or normal density function. All right, so this one is defined as P u of small u equals to 1 divided by under root 2 pi sigma exponential u minus u mean square divided by 2 sigma square, and with a negative sign. So here the sigma represents the standard deviation, or you can write this sigma square represents the variance, okay, of the random variable. This u bar represents the mean, okay. The other one, which is very useful, is Poisson density function. All right, so this Poisson is basically a discrete form of density function. K equals to 0 to infinity k to the power minus k divided by k factorial exponential minus k average and delta u minus k. Okay, so there is only one parameter here, which is k bar. So this one is your sorry again. Okay, this is the mean value of the random variable k. So this is your random value. Okay, so now next we will be studying the joint random variable, okay, and some more properties of probability distribution function, okay, and we will also introduce the Bayes rule, which is also important for this machine learning things, and then the moments of random variable, okay. And I hope that's enough information for the next video, and we'll just continue after that, okay. So thank you for watching.